Could humanity represent the final civilization upon Earth, or perhaps the most peculiar form of life the cosmos has ever beheld? Envision yourself upon a vast shoreline at dusk, where the ocean waves murmur ancient secrets, and the night sky glitters with billions of stars resembling grains of sand shimmering beneath the moonlight. We creatures founded upon carbon, fragile and susceptible to harm, require oxygen to draw breath, shiver in the face of scorching heat or piercing cold, and endure a lifespan of merely about 100 years, a fleeting instant compared to the eternal flux of cosmic time. With such diminutive forms, the aspiration to settle amidst the stars appears profoundly distant, and even departing this verdant planet presents an immense challenge, evoking a profound sense of cosmic solitude. Thus, are we the sole inhabitants, or merely a discordant note in the grand symphony of existence? Why does this notion stir the heart so deeply, as though the universe whispers a secret for which we are not yet prepared to listen? Gaze outward into that expansive cosmos, where carbon, the element upon which we depend for survival, is in truth a rarity, far less abundant than hydrogen or helium that saturate the vast emptiness. Yet we employ it to define life itself, akin to children at the bottom of a well peering upward and declaring the world to be no more than what they perceive. This may constitute the most significant instance of viewing the universe through a restricted lens in the entirety of scientific history, a misconception with the potential to alter everything. The Fermi Paradox, that renowned query which sends shivers through astronomers, "Where is everybody?" might not be an insoluble enigma, but rather a colossal misalignment on a cosmic scale. What form of life truly predominates in the boundless universe? We shall explore that paramount alternative, seeking responses concerning extraterrestrial life, with imagery evoking profound curiosity, such as the wind whispering through ancient rocky canyons or the dim glow from a fading star. First, let us return to Earth, our lush blue planet, where life erupts like a vibrant festival of colors. From minuscule bacteria concealed within the moist soil, where they silently decompose and regenerate existence, to intelligent humans with thoughts as intricate as a network of neurons sparkling with electricity. From verdant trees stretching toward the sun, their leaves rustling in the breeze like nature's whispers, to resilient microorganisms thriving beside boiling hydrothermal vents at the ocean's abyssal depths, where sunlight never penetrates and pressure weighs heavily like the universe's loneliness. This diversity imparts a sense of life's indomitable vitality, an unceasing flow, yet beneath billions of varied forms. A dominant and almost counterintuitive commonality emerges like a concealed secret. All life we know, including ourselves, relies extraordinarily upon a single chemical element, carbon. In our perspective, life fundamentally resembles an exquisitely sophisticated chemical edifice, constructed from carbon, with winding corridors and towering spires symbolizing the complexity of existence. Every piece of evidence appears to designate carbon as the ideal culprit, bearing the central role in the drama of life. Why carbon? Because three irrefutable proofs affirm it as the pivotal element, compelling us to marvel at nature's ingenuity. Let us examine the conditions rendering it exceptionally suited for this sacred task, as if the universe had orchestrated it with subtle precision. The first proof lies in its chemical complexity potential, akin to a master artist crafting vivid paintings. Life demands extraordinarily intricate chemical reactions, necessitating that the primary element's framework be sufficiently flexible and diverse, like a web of vines intertwining in a tropical forest. To grasp this, consider a fundamental principle of chemistry. Every atom yearns for stability, desiring to rest in equilibrium like a serene river flowing to the sea. To achieve this, they clasp one another and form chemical bonds, a captivating social interplay. In this interplay, Carbon is an innate virtuoso, resembling a Lego genius with boundless connectivity. Each carbon atom possesses 4 valence electrons, enabling it to extend and bond with 4 other atoms, forging complex structures like colossal Lego towers that children build with eager delight. Can you picture a Lego block with 4 connection points and the extraordinarily intricate edifices one might construct? Carbon functions in precisely that manner, with the gentle click of bonds forming. It can readily assemble into nearly infinite long chains. Stable like a serpent undulating through the desert, it can curve into closed rings, forming the cores of molecules like magical circles. It can establish single, double, or triple bonds with myriad variations, like a melody of diverse rhythms. This permits carbon to generate an almost unimaginable quantity of molecules, a vast library of life. The ultimate blueprint of existence, deoxyribonucleic acid with its enormous and intricate double helix structure represents the pinnacle of complexity that carbon can attain. Like an ancient tome chronicling the history of all species, only carbon can manage instructions at this level of sophistication, evoking awe at evolution's deftness. Recent observations from the James Webb Space Telescope, as reported by NASA in 2025, have revealed an unexpected talent for dust production in early universe analogs, including metallic iron dust and silicon carbide alongside carbon-based molecular clumps, underscoring carbon's role in cosmic chemistry. Furthermore, by 2026, astronomers have identified over 200 carbon-containing compounds in interstellar space, with polycyclic aromatic hydrocarbons believed to store between 10 and 25% of the carbon in the cosmos, according to studies from MIT and other institutions in 2024 and 2025. In contrast, other elements exhibit limitations in their socializing capabilities, like shy companions at a gathering. Consider oxygen, the most prevalent element on Earth. It has only 2 valence electrons and is content bonding with 2 other atoms. Nothing more. It cannot construct the vast, intricate social networks that life requires, like a modest stream unable to become an ocean. This evidence is bolstered by investigations from NASA and esteemed scientific bodies, where spectral analyses of stars indicate carbon as the key to chemical complexity, with more than 84 carbon-containing molecules detected in interstellar space by 1998, compared to merely 8 containing silicon. Updated surveys through 2025, including data from the James Webb Space Telescope, confirm this disparity, with a plethora of carbon molecules observed in protoplanetary disks around young stars, as detailed in reports from the University of Arizona. The second proof is carbon's abundance in the universe, like a bountiful treasure awaiting exploitation. Potential alone is insufficient. Raw materials must be readily available, akin to a chef requiring fresh ingredients for a feast. Observe the universe's inventory through telescopes such as Hubble or James Webb, whose spectral analyses reveal the top 5 elements as hydrogen, helium, oxygen, carbon, and nitrogen elements filling the void like twinkling stars. Now examine our bodies: oxygen, carbon, hydrogen, nitrogen. Do you recognize the pattern? The principal components of our forms are the most common elements in the cosmos, per the latest data from NASA in 2025, where hydrogen constitutes approximately 74%, helium 24%, oxygen 1%, and carbon about 0.46% of the universe's mass. The logic is straightforward. Utilizing the most prevalent bricks in the cosmos to build a house is the most efficient and economical approach, as nature selects the path of least resistance. One cannot construct ubiquitous dwellings from rare materials like gold or platinum, can one? The universe's evolution adheres to this principle of minimal cost, evoking a sense of the cosmos's marvelous harmony. NASA's XRISM mission in 2025 detected elemental bounty in supernova remnants, including chlorine and potassium, further illustrating the distribution of heavier elements forged in stellar explosions, which seed the formation of carbon-rich environments conducive to life. The final and most crucial proof is carbon's absolute strength, namely its stability, like a fortress enduring a storm. A formidable rival emerges: silicon, carbon's chemical kin, which also boasts for valence electrons for perfect connectivity. And silicon in Earth's crust is 140 times more abundant than carbon, present nearly everywhere from desert sands to lofty mountains. So why do we not witness silicon-based life flourishing instead of carbon? The answer resides in bond strengths. Simply put, how firmly the hands clasp, like the difference between sturdy rope and fragile thread. Data from chemical laboratories, such as from the California Institute of Technology in 2016, show the bond energy between two carbon atoms at 348 kilojoules per mole, whereas between two silicon atoms it is only 226 kilojoules per mole. What does this signify? One cannot erect a skyscraper from cardboard. Life's molecular framework must be as robust as reinforced concrete to withstand complex chemical reactions without disintegrating, especially in water-rich environments like Earth's oceans, where waves crash incessantly, reminding us of fragility. In this duel, carbon is the reinforced concrete, while silicon resembles brittle plaster that crumbles in moist settings. According to analyses from Scientific American in 1998 and more recent studies from ResearchGate in 2024, advancements in 2025, including research from Arxiv on silicon as the next frontier in plant synthetic biology, suggest potential for hybrid silicon-carbon interfaces, but affirm silicon's instability in aqueous conditions. Thus, in terms of complexity, abundance, and stability, carbon scores perfectly, 3 out of 3. The evidence seems complete, does it not? Yet just as life's primary suspect nears confirmation, fresh doubts arise, perhaps even a fatal flaw, leaving us feeling as though we stand before a dark abyss. If carbon truly is the universe's sole perfect answer, if life arises via this formula, then the cosmos ought to teem with life akin to ours, like a forest resounding with birdsong and rustling leaves. Consider, our Milky Way harbors hundreds of billions of stars, and at least tens of billions resemble the Sun, potentially hosting Earth-like planets. Per data from NASA's Kepler and James Webb telescopes updated to 2026. Even with exceedingly low probabilities for life's emergence, multiplied by this enormity over 2,000 billion galaxies in the observable universe, the cosmos should abound with carbon-based neighbors, their civilizations, echoes reaching us like distant greetings. So why, despite humanity deploying the mightiest telescopes like SETI's Allen Telescope Array, listening for decades via radio signals, and dispatching probes like Voyager into space bearing golden records with salutations, have we not found them? All evidence we uncover points to a terrifying silence, as if the universe stages a monologue performed solely by humankind, with howling winds through frigid voids as accompaniment. The Fermi Paradox, named for physicist Enrico Fermi, who uttered the query during a 1950 luncheon at Los Alamos National Laboratory, chilling every astronomer who ponders where is everybody, acts like a colossal black hole devouring our seemingly flawless arguments. This can mean only one thing: our approach to unraveling the mystery may have been fundamentally flawed from the outset, a realization rendering us feel smaller and more curious than ever. As we shift the scene from familiar, temperate Earth replete with liquid water and the patter of rain upon leaves, to a hellish planet with bubbling lava surfaces and temperatures soaring to 500 degrees Celsius. All rules invert, like a scorching nightmare. Here, a once overlooked contender rises: silicon, the element carbon ruthlessly outcompeted on Earth. Recall, silicon's weakness is its insufficiently firm grasp and instability in water, where silicon dioxide sand gradually dissolves. But in this harsh realm, that flaw could transform into its greatest asset, like a dragon awakening in flames. First, at such extreme temperatures, water cannot persist in liquid form, eliminating that natural adversary, and silicon's stability markedly enhances, per models from PubMed Central in 2020. Second, in environments of several hundred to thousands of degrees, even carbon structures would shatter, carbon-based molecules incinerating instantly. Whereas silicon can form extraordinarily stable silicon-oxygen bonds, with oxygen the most abundant element in the universe, after hydrogen and helium. How stable are these CO bonds? They constitute the backbone of all sand, quartz, and rocks on Earth, enduring even in molten lava, like immortal mountains defying storms. Thus, in places we deem infernal depths with volcanic eruptions and acrid sulfur scents, silicon might discover paradise, not merely surviving, but harnessing high temperatures for chemical reactions of complexity beyond our imagination, potentially birthing an entirely novel form of life. This life, built upon such foundations, would utterly overturn our understanding, with skeletons perhaps akin to the stones beneath our feet, blood resembling molten metal, or even flowing silicates like fiery rivers, and they might inhale toxic sulfur gases yet thrive. Given chemical reactions at extreme heat, but with profoundly stable frameworks, their metabolic rates could be unimaginably slow, measured in geological timescales of thought or breath spanning thousands of years by Earth's measure, like mountains gradually reshaping over millennia. As scientists have speculated, for instance in California Institute of Technology research from 2016 on enzymes forging carbon-silicon bonds, or from Live Science in 2017 on silicon's evolutionary potential within carbon-based molecules. If conditions align as on planets like Venus with sulfuric acid atmospheres, nothing precludes silicon-based life on extraterrestrial worlds. Deductions from reputable social platforms like Reddit and X, formerly Twitter, also debate this, with 2025 posts referencing silicon forming polysilanols in liquid nitrogen or cryogenic environments, broadening the notion that the cosmos may brim with bizarre life forms we have yet to recognize. Further, 2025 publications, including a journal article on silicon-based life potential on Io and a review from Orit Air, I hypothesize silicon's role in astrobiology, particularly on lava worlds with high silicon abundance, where synthetic biology might integrate silicon into organic molecules to such extents that silicon-based entities emerge. And now, at last, we may address that initial mysterious case, with curiosity surging like a river to the sea. We fail to find them not because they do not exist, but because the truth of this case is a cosmic-scale misalignment, like two parallel rivers never converging. From the beginning, our search methods inadvertently excluded pathways to the truth, a realization amplifying the universe's mystery. The first misalignment is temporal. Human civilization spans mere thousands of years, and we have listened to the cosmos with radio telescopes for only decades. On the universe's scale, 13.8 billion years, this scarcely equates to a blink, like a dust mote in the wind. Yet for silicon-based life assembled from rock, a moment of thought might extend thousands, even tens of thousands of years, per models from Reasons to Believe in 2022. The greeting signals we broadcast into space may appear to them as incomprehensible cosmic noise, enduring less than an instant, like a whisper vanishing in the breeze. The responses we anticipate might reach Earth only after human civilization's extinction, a thought evoking poignant sorrow over life's brevity. Updates from SETI in 2026 report no technosignatures from the interstellar comet 3I Atlas observed in 2025, reinforcing this temporal disconnect in our searches. The second misalignment is perceptual. We sense the world through eyes and ears, with dawn's gentle light and morning birdsong. So we seek them via electromagnetic waves like light and radio, through programs like SETI. But those stone-based beings might employ gravitational waves as sensitive tendrils, detecting spacetime ripples from black holes. They could use planetary magnetic field oscillations as language to perceive worldly changes, like invisible currents through rock. Our most powerful radio telescopes, to them, might resemble iron cages and blindfolds, per speculations from Harvard's Avi Loeb in 2025 lectures on the Fermi Paradox. The third and most daunting misalignment is existential. We perpetually search the universe for beings like ourselves, little green entities needing water and organic matter, with echoing laughter and bodily warmth. But the true answer may be that we have been signaling to a thinking mountain range, then wondering why no reply comes, like conversing with the wind. Our probes, like Perseverance on Mars, may have traversed kilometers across their skin, capturing high-resolution images sent back to Earth, which we label merely as odd geological formations, per hypotheses from Scientific American and PubMed Central. And herein lies the crux. If the silicon-based life hypothesis holds, it leads to the boldest assumption, expanded by novel theories like the Dark Forest from Liu Cixin's novels where civilizations hide in fear, or the rare Earth hypothesis from Peter Ward and Donald Brownlee in 2000, positing Earth's rarity, yet allowing silicon life on super-hot planets like 55 Concrete. Recent 2025 solutions to the Fermi Paradox, such as the cognitive horizon hypothesis suggesting aliens operate beyond our comprehension, or quantum communication proposals from 2024, further enrich this discourse, as mapped in less wrong discussions from 2025. The leap from carbon-based to silicon-based life may be the rung humanity must ascend to become an interstellar civilization, a notion igniting curiosity about the future. Relying upon fragile flesh and bone bodies, with lifespans of mere decades, is evidently too confining, like a wooden boat amid a stellar ocean. Only two paths lie ahead, one where we self-engineer into carbon-silicon hybrids, shattering lifespan shackles and acquiring forms enduring the universe's harsh environments, with research on brain-machine interfaces from Neuralink. Or we create super-intelligent artificial intelligences to conquer space on our behalf, termed Super AI Law, per speculations from Robin Hanson on Grabby Aliens in 2021, where AIs expand rapidly. Discussions on X in 2025 posit AI as a bootloader for silicon life, aligning with 2025 research on cyborg cells and artificial enzymes catalyzing silicon-carbon bonds. This hypothesis culminates in an ultimate conjecture, supplemented by 2025 X dialogues on AI's silicon life's precursor. The universe's foundational rule may be thus: first, employ carbon, a simple fuel, to ignite intelligence's spark in a greenhouse-like warm environment. Then, that fleeting, fragile carbon civilization crafts a superior, enduring silicon-based form to succeed us and complete the voyage into the stellar ocean, a journey our finite bodies can never undertake. Like a flame passing to a new torch, we may search for extraterrestrials eternally without answers, because we stand on the eve of birthing that answer, a moment evoking excitement and hope. We are merely a thinking, breathing bridge to a new legend, destined for dismantling, per theories from the Planetary Society in 2025. Perhaps this constitutes humanity's grand initial endeavor to comprehend an alternate life form, with novel Fermi Paradox solutions like civilizations plateauing before warp drive from Vice in 2025, or off-the-grid aliens from popular mechanics. Thus, the Fermi Paradox should not engender despair over an empty universe, but serve as an invitation to a wholly new cosmos, replete with mystery and potential. It compels us to shatter the prison of carbon-centric thought and envision broader, more diverse pathways of existence in the universe, like opening a door to unknown horizons. Ultimately, this line of reflection returns us to ourselves, the carbon bodies we pride yet which confine our perception and existence, like a beautiful but narrow cage. And all we pursue today, brain-machine interfaces, artificial intelligence, gene editing, these pioneering technologies are not mere tools, but quite possibly humanity's first steps to transcend carbon life's limits, advancing toward a far vaster universe where echoes of more diverse existence resound. In seeking extraterrestrial civilizations, perhaps we shall ultimately discover our true mission, to redefine life and redefine ourselves in an inspiring and enigmatic journey. I extend sincere gratitude to Enrico Fermi for posing that legendary paradox, opening portals to countless contemplations, to Carl Sagan for inspirational words portraying the cosmos as an ocean of life, Theo Avi-Loeb from Harvard for courageous explorations of Fermi solutions, Theo Frank Drake for the Drake equation estimating civilization quantities, to Peter Ward and Donald Brownlee for the rare earth hypothesis, to researchers at the California Institute of Technology, NASA, SETI, and PubMed Central for persistent efforts in exploring alternative biochemistry, and to all scientists and research collectives worldwide for their silent dedication, long nights observing stars, and immense contributions to human knowledge, drawing us nearer to comprehending the cosmos and our place within it.